How many ordered pairs of positive integers b, c exist where both the quadratic equations x squared plus bx plus c equals 0 and x squared plus cx plus b equals 0 do not have distinct real solutions? All right, distinct real solutions. All right, if they don't have those, then we must have that either we have two identical real solutions, right? Right? Basically, if the solutions are not distinct, then that satisfies it. Or we could have two imaginary solutions. So those are our two cases, right? And notice how this corresponds to the case where, right, the discriminant is 0, and this is like the discriminant is less than 0. Essentially, what I'm saying is, when we look at the quadratic formula, negative b plus minus a square root of b squared minus 4ac, and since a is 1 here, we just write 4c over 2 times a, which is also 1. So if you look at this, right, two identical solutions means that the plus minus actually does nothing. In other words, this is equal to 0 either way. And if we have imaginary solutions, that means this thing inside is less than 0, okay? So what we're saying is b squared minus 4c is less than or equal to 0 and c squared minus 4c, or c squared minus 4b is also less than or equal to 0. We use these two equations to try and bound our pairs here, because first of all, notice how we can write that b squared is less than or equal to 4c, so c is at least b squared over 4. And similarly, we also have b is at least c squared over 4. And we can do a simple substitution. Since c is at least b squared over 4, we can plug in b squared over 4 all into c and get a value that is smaller, even smaller than c squared over 4, right? Just like that. So we actually have this two inequalities that we can kind of mash together by doing this substitution. This only works because we have two, right? These are the same direction. Otherwise, we can't make this substitution. Anyway, this gives us b to the 4 over 64. So since b is a positive integer, we can divide by b and multiply by 64. And we get that 64 is greater than or equal to, right, b cubed, or b is less than or equal to 4 in this case, right? So I kind of just like flipped them, but I made sure to keep the inequality sign in the correct direction at all times. So we get that b is less than or equal to 4, which also means c is less than or equal to 4. So now we take a look at what it's asking, right? We have positive integers, b and c. So that limits our choices a lot, actually, because if you look at this, there are only so many choices for b and c, right? They can only be 1, 2, 3, or 4 for each of these, which is kind of good because now we can just look at each case separately, right? All right. So to do this, I'll put a check whenever it satisfies these two constraints, okay? So first of all, let's take a look at the cases where b squared minus 4c is greater than 0, right? Essentially this. And then we can subtract those out from our total, right? Because those will not work. So if we take a look here, if let's say b is 1, then 4c is less than 1, which gives us no solutions. If b is 2, then we get c is less than 1 again, but 4c is less than 4, so c is less than 1, also no solutions. So this doesn't take out any cases, but if b equals 3, then we get that 4c is less than 9, or c is less than 2.25, which means that the cases where b is 3 and 2, or 3 and 1 are both bad. So we just take those out quickly. So those don't work. If b equals 4, then we see that basically we get that 4c is less than 16. So basically this rules out c equals 1, 2, or 3 for b equals 4. So these are also bad. And symmetrically, right, we can say that these will not work for the second equation. Everything that I did not put an X on, those are fine, meaning that they satisfy both B squared minus 4C is less than or equal to 0, and C squared is minus 4B is less than or equal to 0, right? So as a result, we can count 1, 2, 3, 4, 5, 6 total solutions, ordered pairs of B and C that work, or in fact satisfy that they don't have distinct real solutions. So our answer is B.